Hi, welcome back. Can't believe it's already finals. So I'm just gonna go through my notes here. Um, I think by the time this video is uploaded, you guys might have already received this PDF file from me. So let's just go through all the chapters that are going to be covered in finals. It's not much, but it's just a bunch of equations that you guys have to familiarize with. Especially when the questions are very vague and not direct. But yeah, so let's just go through the first part. Chapter 4 is basically a continuation of chapter 3. I forgot what chapter 3 is about. Wait, no, chapter 3 is about the ideal ideal gas calculations, and and there are several equations that comes after, like the cubic equations, the EOS, and then the Lee Kessler. All these calculations, all these formulas, the measurement of how much the real thermodynamic, no, the real properties, like pressure. uh, I think it's a Z value. It's just a measurement of how much it deviates from ideal gas. Let's say you have a volume of it. Let's say when you use PV equals to nRT, PV equals ZRT. For ideal gas, you assume Z equals to 1, right? But there comes this equation of Lee Kessler, cubic equations, the EOS. These equations, how much the real volume deviates from ideal gas. So let's just go through heat effects. So heat effects is just not much. Basically, these are the important stuff that you have to familiarize with, which is the heat capacity in ideal gas state, evaluation of sensible heat integral, and the standard heat of reaction. So basically, when we want, when we have a system, when we have a system of, let's say you have a box here, and you have, let's say you have methane, right? And then you at first it has temperature of T1, and then as you heat it up, you have, it's heated, right? So you have T2, CH4. So when we want to calculate the total heat and total enthalpy change in this, when CH4 is heated up, we are going to assume it as ideal. Why we don't assume it as real gas? There will be another chapter coming forward where we incorporate real gases calculation, but for now we are just going to assume it as ideal gases to make our job easier. So when we heat up CH4, there is going to be an enthalpy change, right? So how do we calculate the enthalpy change? Is just by using this equation, the heat capacity in ideal gas state. So where we calculate from T1 to T2, and then CPIG over R, which is technically A plus BT plus CT squared plus DT negative 2. These are all from the tables of table C1, so it's not going to be really complicated. But then here comes the evaluation of sensible heat integral. Really, you're going to only use this formula when we don't have final temperature. Let's say you have the same box of methane of CH4 at T1. We have a known value of A, let's say, and then you heat it up. You have a box of CH4 again. You heat it up to temperature 2, but we don't know what it is. But say probably this is going to be won't be just one species. It's going to be a whole system. Say you have, I'm just going to write it here, because it's going to be a combination of heat of formation and also heat of reaction. So let's say you react something with something. You react A plus B to get C plus D, right? So yeah, first you have a temperature of T1, and then at the final reaction you have temperature of T2, right? So there is going to be an enthalpy change, and there will be also heat of formation, because you are forming these products, because there's a reaction and then you are going to produce a product, right? So let's say you have um, a system of A plus B, and then here usually it will be heat of reaction. Let's say of T1 you have, say, 373K, and then at and then but you don't know the final temperature, right? But here comes the tricky part. When you want to calculate the enthalpy change when there's a change in temperature, you have to assume it as ideal gas, right? And this table, the ideal gas state, our reference state should be 298K. So if the initial temperature is 373K, you have to bring it down to 298K. But this is still A plus B because we haven't formed any product, we're just changing temperature, right? So this is just going to be your HR, heat of reaction. And then you're going to form those products. So at T equals 298K, because we are assuming it as ideal gas, right? So when we form a product, there will be heat of formation, right? Correct. But here comes the problem. You are going to bring it up to an unknown temperature, C plus D. From 298K, you're going to bring up to, I don't know, we don't know the final temperature. So what we're going to do is, usually the question will ask, what's your max temperature? So we are going to assume it as when at T max, Q is going to be 0. So you have HR plus HF plus heat of product equals to 0. We know the value of heat of reaction because you can just find it using this CPIG, right? And heat of formation, we can also find it from here, the table C4. So this value is known, but we don't know the HP. So your HP will be from just algebra. You can just find it, and then you use this sensible heat integral to get what is it? I think it's HP. The final formula should be HP, and then R, the sensible heat integral, plus T naught. Yeah. So that is heat effects. I don't think this is going to be important, this rule here, because that is just latent heat of pure substances, basically when you are changing phases. But I haven't seen any question that talks about change of phases, so let's just move on. So next is chapter 6, thermodynamic properties of fluid. Okay, this is going to be a lot to cover, so let's just take it slow. So basic common knowledge, basic thermodynamic knowledge. Thermodynamic properties, you have what? Enthalpy. You also have S, entropy. You also have Gibbs free energy. This is G. So I don't think I need to cover this because this one you can find the same table as heat of formation, table C4. Entropy, what is the formula again for entropy? For ideal entropy, it's Cp Ig over R dt over T plus R ln P over P naught. This is T1 to T2, and then H is just from before. So these are your thermodynamic properties, and this is your Gibbs free energy. Okay. So from before, since we are assuming ideal gases, right? Wait, hold on. Yeah. So we know that. So what is really Gibbs energy? Gibbs energy is just the maximum work done. Gibbs energy is to calculate the maximum work done when given that the temperature and pressure are constant. Yeah, temperature and pressure are kept constant. The formula is this one. But really, you don't really need this formula because your Gibbs free energy, you can just find it from this table C4, and to find the total Gibbs free energy is the same as finding heat of formation, which is Gibbs free of product minus Gibbs free of reactant. So now let's go on to residual properties. So remember when I said from chapter before is that why we are only assuming ideal gases and not real gases. So here comes the part where we assume the system as real gas. It's not that really complicated. Basically what we are doing is we want to find the residual properties. So basically residual properties is we want to know how much the real thermodynamic properties deviate from the ideal part. We want to know so basically from this equation here, mr equals to m minus mig, where m is basically any thermodynamic properties. It can be enthalpy, where h minus hig, or it can be entropy. It can be any thermodynamic properties. So what we are doing here is that we want to know how much does the real value of enthalpy deviates from the ideal entropy. That's basically it for residual properties. Yeah, so what is really important here is that, so from before we have a system, right? A plus B equals to C plus D, where there's a reaction. At T1 we have, say, 298K, and at T2 is 373K. So what we are going to do is that when we have A plus B, we are going to assume the starting state as real gas, unless the question specifies. But I'm just going to talk in general. When the question doesn't specify your system starts from real or ideal, we're just going to assume it starting from real gas. So what we do is we want to change it to ideal gas. So A plus B ideal, we have the same T1 and we have the same T1, because we're not changing temperature yet. We just in a simpler terms, we are going to make the real gas into ideal gas, but we are not changing any temperature yet. So A plus B plus CD, actually this is going to be hard. I'm just going to give you an example from past year, where you only have a system of A, and you have T1, which is 298K, and you have the same, and you heat it up, so you have 373K. So first, if the question never specify anything, we're just going to assume it as real gas. So real gas, and T1 is 298K. So we are going to assume it as actually I'm just going to, let's just put that as 320K, and then we have A ideal of P1 320K, and then we have A ideal. We are going to change it to 373K, and then we're going to bring it up to real again at T2 373K. So uh, yeah. Okay, yeah. Okay. So what the hell, right? Yeah, what the hell. Okay, so this is going to be your H1R, this is going to be your HIG, and this is going to be your H2R. Okay, what the hell, right? So here's the thing. um since this whole chapter is about residual properties meaning that we are measuring how much the real properties deviate from ideal properties. So let's see, when we have a system of A, which is real gas of A, um, when we want to calculate the change in temperature, there's only one way, which is CPIG over R, right? So we can't find the change in temperature unless the system is in ideal gas. So say you have a real gas at the start and you have another real gas at the second state of 373K. So how do we want to calculate the change in temperature of real gas? We can't. We can, but we can't calculate directly. You have to change it to ideal gas, and then only we can and then only we can find the change in enthalpy. Correct? So, first you have real gas of 320K. What we're going to do is we're going to change it to ideal gas first. So what we do is we have these residual properties of from before. How do we want to find the HR? Is that we have two ways where we can use generalized property correlation, or we can use second virial coefficient depending on the questions, um, which method they want. So you have to keep an eye on that, whether they want second virial or they want generalized property correlation. So say you have say they want second virial coefficient. So you have to use this method, you have to use this working, which is HR or RTC equals to blah blah blah, and then you can find the real enthalpy to change it to ideal gas. Next, the next step is, since from state 2 to state 3 is ideal, both are ideal, so now you can find the change in temperature, which is just HIG from before. And then how do we want to calculate ideal? How do we want to know the enthalpy, real enthalpy, when we change from ideal to real? Is by using the same thing, which is from this equation. So, and then the question will finally ask, what is your total enthalpy? Your total enthalpy will be negative HR plus HIG plus H2R. Just remember to put a negative here because we are changing from real to ideal, so it has to be negative. But when we want to change from ideal to real, it's positive HR. Just bookmark your textbook. I can't remember what pages is it, so you kind of have to go through and then bookmark the formula. So, but these are just the essence of it, of residual properties. Okay, now let's move on to what the fuck. Okay, no, I don't think this is really important, so we can just skip it. So next is fugacity and fugacity coefficient. Look guys, starting from here, I think starting from chapter 11 up to chapter 13, I think you guys are a bit scared or intimidated to tackle the questions. But guys, it's just bookmarking your formulas and they're just plugging in all the values from tables. It is really not that hard. It takes a long time to do because you have a bunch of tables that you guys are going to be looking through and a bunch of values. So I recommend you guys to take your time to really understand the usage of formulas, because it's really easy to get marks here. Yeah, so I hope when I explain all these formulas, you guys uh, will be more familiarized by using these formulas during the exam. So just make sure when you guys are watching this video, make sure to go through the textbooks at the same time, so that you guys can bookmark the formulas that I highlighted here. So yeah, where was I? Okay, chapter 11, fugacity and fugacity coefficient. Look, guys, the thing is, fugacity is really a huge idea that I can't really simply define by a single sentence, but to just make it simple, um, when we have an ideal gas, right? When we have an ideal gas, say you have CH4 and you have a fixed pressure of 4 bar of CH4. So what fugacity really is that it is, how do I say, it is the pressure of a real gas that corresponds to the pressure of an ideal gas. So what it basically means is that maybe you can, I don't know, understand it as the real pressure of a system. Let's say you have 4 bar, let's say you have an ideal gas of CH4 that has the pressure of 4 bar, but the fugacity or the real pressure would be somewhere around what, 3.2 bar. Yeah, so that is really what fugacity is. But fugacity is defined as the tendency to escape, I don't know how it corresponds honestly, but let's just go through. So so it is really not that hard. There's really only two formulas that, not exactly two formulas, there's exactly two methods of determining fugacity that you have to know, which is second term virial coefficient, and also this long as method, which is generalized coefficient. This whole thing is called generalized coefficient. These are just derivations of it, but what really important is this one and this one. So let's go through one by one. When this question says to calculate the fugacity of a second term virial coefficient, what you just have to use this, and then you need to find the fugacity coefficient. Basically, fugacity coefficient is just the ratio of hold on. Ratio of fugacity, or the real pressure over pressure of the system. So fugacity is actually just fugacity coefficient is just technically the ratio of fugacity to the real pressure of a system. So you have fugacity over P. P is the pressure of a system. So from these two methods, you need to find the fugacity coefficient, and then from there you can find the fugacity. So from this you can find fugacity coefficient, and here also you can find the fugacity coefficient. So I might have missed a step here. Basically, after you have find your fugacity coefficient, you have to find your fugacity, right? So fugacity is actually fugacity coefficient times the mole ratio times the real pressure, pressure of a system. These are the final step that I forgot to write. Yeah, that's just it. Yeah, don't think I missed anything. Yeah. Okay. Did I miss anything here? No, don't think so. Okay. Okay. Um. Damn. Okay. So, so you guys have determined the fugacity of a system, right? Say you have. Um, I'm trying to relate these two chapters, but honest to God, I don't know how am I supposed to relate this thing. Okay, so say you have um hmm, damn. I think I should have explained this thing first, because then it will be less unbearable to comprehend this. But here's the thing. Okay, say you have a say you have a system, right, of a mixture. You have A and you have B, and both have B vapor and B liquid, and you have A liquid, A vapor. And for this, you have your own mole ratio, right? Because these are the same system. Um, you have mole ratio for vapor, you have mole ratio for liquid, right? So what we do is, what Raoult's law is trying to tell you, is how fugacity and fugacity coefficient uh, is related to the vapor phases and liquid phases. So, and it is only valid for pure species in ideal gas state. But if we want to calculate for real gas, then you have to kind of modify the Raoult's law to incorporate real states. So, um, damn, how does one even become a thermodynamics lecturer at this point? Because how do you even explain this concept? Um, yeah. Okay. Guys, I just think that you guys have to just go through these notes and understand one by one. But yeah, for Raoult's law, this is bubble point calculation and dew point calculation. I'm not really sure if this is gonna come out in finals. I'm just putting it here so that you guys know how it relates to one another. But this is Raoult's law. These two are Raoult's law. Sorry, this is modified Raoult's law. This Raoult's law. Basically, Raoult's law is just a method to determine um, the mole percent of vapors of a species in vapor state and liquid state. That's why you have bubble point calculation and you also have dew point calculation. But really, it's just matter of plugging in formulas, so it's really not that hard. But yeah, honestly, I think for chapter 11 and 12, it's just mostly plugging in formula, because really it's really hard to explain this concept in a very simple manner, because it's really not that simple. I'm not trying to sugarcoat anything. It's really hard to explain this concept in a very simple terms, because it's really deep, and I'm not even joking. So I don't even uh, understand mostly. But you just have to memorize this formula. Not really memorize, just bookmark this formula, this Wilson equation and Margulies equation. This is just a method to predict the activity coefficient, and when you find the activity coefficient, then you can find your pressure of a system, and also your yi, which is the mole percent or the mole ratio for, I believe, vapor state. Yeah. And then obviously from vapor state, and then you can find um, liquid state, right? But here's the thing. Okay, let me just go through the formula. So in Wilson equation, sometimes they've they've already given x1 and x2, I think. Yeah, x1 and x2 is already given. So you just have to find your a12, which is this formula. You just have to find this p1 set and p2 set from at first. Find p1 set and p2 set of vapor pressure, which is ln p set equals to a plus b over t plus c. Correct me if I'm wrong, but this is Antoine equation, if my memory serves me right. And then from that, you can find your a12 and a21. Usually your v2 and v1 is already given from question, as well as negative a12. RT is your gas constant, and T is temperature of the system. And then from there, you can find your activity coefficient, your gamma 1 and gamma 2. After you find this, you can find this and this. And then from there, by using modified Raoult's law, yeah, I really recommend you guys to look through Raoult's law, because it's really interesting to understand really well. You guys have to go through Raoult's law. I don't really know how to explain in simple terms. If I explain, it's gonna take more time. So yeah, and then you have Margot's equation. The same steps, except from finding activity coefficient. These two, if you notice, this and this are different. So what's really different from Margot's and Wilson is just your third step, honestly. Just the third step is what's missing and what's different. And then moving on to chemical reaction equilibria. Then I'm just going to highlight what's important. What's important is the reaction coordinate. Just remember to understand this really well. Yeah, so basically what is reaction coordinate? Reaction coordinate really shows you the progress of the reaction. Say you have A plus B plus C, A plus B produce C plus D. So what reaction coordinate tells you is that whether it just really tells you the progress of the reaction. Say at first you have 1 mole of A and 1 mole of B. So reaction coordinate tells you that the reaction is probably still ongoing to produce C plus D. So at first C has 0 mole, D has 0 mole. So reaction coordinate is there to tell you the increment of production of products. So say from C you have 0 mole, and then it becomes 2 mole. So the reaction coordinate tells you, oh, first you have 0 moles of C, and then you have 2 moles of C. So that's just reaction coordinate. And then you have effect of temperature on the equilibrium constant. I think it's much easier if I go through questions for chapter 11 up to 13. If I'm just gonna yap, you guys won't understand anything. So these are what's important, honestly. This one and this one. Sometimes they'll ask you the effects of temperature and pressure in equilibrium conversion, or is it constant? Man, yeah. This is important. Just remember to mark in your textbooks. Yeah, this is important and this is important. This is important and this. Yeah, so basically that covers every chapter in Thermo. See you. I'm just gonna go through I'm just gonna do another video where I cover final paper, past year question.